Okay, hello everybody. My name is Matt. I'm going to be your moderator today. So hopefully you can all hear me. If you can, maybe type in hello. Excellent, that's good to hear. Okay, I'm just going to go through a couple of slides just to show you the system we use, and then I will hand over to Paul. At the moment there's no video, so don't worry, we'll turn that on when we start. You probably don't want to see me on the video. Okay. So, just to point out the system, so on the right hand side, this is what you're looking at the moment. This is where the slides appear. In the top left hand corner, you'll see the chat window. On the in the top left corner is the participant list. In the middle is the chat window, and at the bottom are the audio controls, so you can turn the volume up if you need to. If at any point during the session you have trouble with the audio, then the best thing to do is go to the Tools menu and run the Audio Setup wizard, and that will basically just run through a few settings and make sure that your speakers are set up for best performance. So, as I said, there's no video at the moment, but when we do start, you'll see a new video window pops up. You'll be able to drag it around by dragging the bar at the top. You can make the video smaller or larger, depending on how big you want it. And if by any chance the video looks a bit grey or grainy, then just make sure the quality setting is on fine colour. Sometimes it gets set to greys accidentally. Okay, one thing to note, there is a chat window, as you've seen on the left-hand side. You can send messages to anybody in the room, or to the whole room, or just to the moderator if you want. Please be aware that this session is being recorded, so any messages that you post will be in the recorded session. Okay, final announcement. There is a certificate of attendance available for this session, and you will find out how to get it at the end of the session. Okay, so we're just going to take a quick break for a second. We're going to swap over to Paul, we'll turn the camera on, and then we'll get going.
Okay. Hi, good to see you. Such a good number there as well, 25. Now, can you all hear me, and can you all see me? Very good. Yeah, I've got a few yeses there, so that's great. Good. Now this session is actually based around Macmillan Maths. It's actually using some of the interactive ideas that I've developed and have written about in Macmillan Maths. But a little bit about myself first. I've been teaching since 1981 actually, so it's a 30-year anniversary this year. Not all my time teaching, but predominantly primary teaching, and for the last 15 years I've actually been writing mathematics books for the UK and with Macmillan for Nigeria and the Middle East, and thoroughly enjoyed it. Most of my time now is spent sort of training teachers, which is great fun. Now, this session is going to focus on the connections that children make between words, images, objects and symbols. Now this is obviously a key way that children actually make sense of mathematics. Haylock and Coburn came up with this diagram. It's been around for a long while, Bruner talked about it and so on, but I think what I want to cover is the importance of the connections between the words, the language, the images, and objects. That's where children actually get their understanding from. And if any of those parts aren't connected, and children don't make the connections between them, obviously they have difficulties with understanding that particular aspect of maths that's being taught. Okay. Now the activities, as I said, are taken from Macmillan Maths, and I'm going to focus on a very specific part, which is the mental and oral starter. Now, when you're making sense of maths, understanding is related to representations, as I said, the images and the models and so on, making connections between those representations. And it's actually within the mental and oral starter that children actually in the UK have made the greatest progress in this last 10 or 15 years. Teachers have actually found it a really useful session, 10 or 15 minutes at the beginning of a lesson, just to keep the children sharp, reintroduce something, remind them, get children to actually to reinforce some of the learning that's gone on before. Okay, so I'm going to pick on some interactive activities and really focus on the language that's used and how it links with images and models. Okay, any questions? Obviously, you know, during it, but at the end I'll try and have a session as well. Okay. Now, one of the first things I'm going to use is to show the importance of an image, okay, a mental image for children, but using an object. And this is something you'll recognise, I'm sure, and some of you may well have used. It's actually a counting stick. Okay, it's a basic counting stick. Now, I'm going to actually use a glove puppet of a small dog. Hope you can see him. Okay, bring it back here a little so you can actually see it. Now, this is a classic empty counting stick which provides a mental image for children. We could have a number at one end, okay, here, up to another end, up to a number at the other end here. So, if this was 0, for example, this could be 10, okay, and we could just count. Now this is going to be interesting. In your own little places, being interactive, I want you counting aloud, if you can. Or you can count by writing the numbers if you want, but counting aloud, okay, with me. So if this was 0 and this was 10, we could just count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so as basic as that. But obviously, there's a bit more to it than that. So we could have any number to start with. So this could be 3. This could be 13. We could count through. The midpoint is really important here. With children's counting, you're trying to get a mental image. So 3, 4, 5, 6, 7, 8. Key number there. The one before, 7, 8, 9, 8, and so on. So going backwards and forwards along this blank counting stick. Now obviously this could be 0, this could be 1. So we could count in decimal numbers, 0, 0.1, 0.2, and so on. Okay. One of you, just to see, we could count in our multiplication tables. Are there any particular tables that you'd like to actually work on? Any practice that you need? Anything that you find difficult to count in 3s or 5s or 6s or anybody there? No? Okay, well I think, yeah, maybe the 7s. Maybe we're counting 7s. So if this ends 0, okay, this could be 70. Okay, so 0, 7, 14, 21, 28, 35. Important one, 42, 35, 42, 49, 42, 35, and so on. Okay, reminding and repeating and so on. Okay, so the mental image of a number line, mental image of a number, counting in zeros, useful, will actually then stay with a child. Actually, when you're then counting in different steps from different starting points, you get the mental image. So the idea of an image and linking to symbols and so on, just as another activity, this is one that children use a lot, teachers use a lot, and this is trying to recognise, with very young children, actually recognising digits, recognising numerals. Okay, so if I just show part of a number, okay, let's see, can you work out which number it is? What number do you think this could be? Type in, anybody, any idea? What number could this be? Anybody? 3? Yeah, it's a decent one. Gregory, yeah, could be a 3. Okay, anything else? Okay, 0, could be a 0. Okay, so we're looking at the features of a number. Okay, what a Marco, right? Any idea now as it's growing up there, what could it be? No longer a 0, could be a 6, very good. Could be a 0, okay, as it's appearing. It's an upside down 5. Okay, so confusing. Let's try one that's more normal. So get children to actually look at missing numbers as well. What about this one? Okay, any idea? Yeah, that's a good shout. Good shout. Could be an 8, could be a 9, could be a 9. We're starting to get into this now. Any idea now? Okay, yes, now we know. So an 8. Okay. One thing that is really interesting with that type of activity, and it shows something that Ken Robinson talked about. I don't know if any of you have seen his TED lectures. Ken Robinson on creativity. He talked about actually children having no fear. Okay, they were prepared to be wrong. They're prepared to have a go. Okay, and we slowly lose that. Now, with that example, if you do it with children, children immediately shout out 9, 8, 6, 4, whatever they're thinking. They're not worried about making errors. And actually, that's one of the key things with children with confidence in mathematics, is to get them so they have no fear of making errors. Now, I don't know about your childhood, but certainly mine, I was a little fearful of maths. Maths tended to be closed questions, maybe individual answers that you were given, you had to give. And if you got it wrong, it was wrong. So somehow changing that culture so that children actually feel, okay, I can have a go. I'm not going to be told off if I get it wrong. I think that's a culture that we need to encourage. And certainly Ken Robinson, when he talked about creativity, he said it was an important aspect. Okay. One of the ways of doing that is to actually get children to be in a bit more control. It's the constructivist theory, but getting them to actually make decisions and not just be teacher-led. Now, Show Me is a type of activity that teachers are using in the UK, I'm sure worldwide, where children actually show an answer to a question rather than responding orally. Okay, so they listen to the language, they listen to the question, they then have time to respond. Okay, so something like digit cards, okay, with the numerals written on. Okay, really useful piece of kit. I tended with my children, my class, children to have a pack of material, pack of resources that they could use. And that included digit cards and number lines and 100 squares. But digit cards are my favourite, 0 to 9 digit card. But the key thing for me is not to have all the digit cards available. You make a decision and get them to use 2 or 3 or 4 digit cards. And with those digit cards, you can then really tailor the types of questions you want to ask. So for example, with a 3, a 4, an 8 and a 7, we could see those as individual digits. So individual numbers or individual digits. If we take them as individual numbers, okay, a question could be, could you show me an odd number? Okay, and a child would hold up the card or just put them on the desk in front of them. So as a teacher, you can walk around and have a look at the answer they've got. And it gives children a little time to think it through. Okay, can you show me a number that is 1 more than 6? Or a number between 6 and 8? Those types of questions. They're quite closed questions. So you could open it out a little. For example, it could be something like, could you show me now an odd number? okay, with any of those digits. So we're now using them as digits. Okay, so we could show, a child might show the number 3, or they might show 43, or they might show 843. And there we have one of the great strengths of an open question. Obviously, if a child shows the number 3, and another child shows the number 843, it shows possibly different abilities. And I think one of the strengths of a primary teacher is knowing the individuals within the class and actually then reinforcing and supporting them through there if the child needs support or needs challenging. And it's catering for those different abilities. So I'll ask you a question and you can respond. So using all 4 digits, or as many digits as you can, could you write down, please, the largest odd number that you can make? The largest odd number with the digits 3, 4, 8 and 7. Have a go. Okay, so the largest that you can make is 7. That's good. Now, is there a larger number using maybe 2 digits to make a 2-digit number, or 3 digits to make a 3-digit number? Okay, 87. Now we're getting there. Okay, anything with 4 digits? What is the largest 4-digit number that you can make? That's an odd number. Well done, Kiklod. Okay, using each digit just once. I'm lucky, right? That's a good effort there, but 8,743 looks pretty big to me, so well done. That's good. So that's the largest 4-digit odd number that you can make just with those digits used once. And remember, the children will be actually using the digit cards to make the number, so they can't repeat each digit. Okay, we'll just take it on a little bit. What about the largest multiple of 3 that you can make? Now, I've added the expression that you can make. And I do feel that actually with children, they need that little bit of a get out so that they can do it at the level that they're happy with. So the largest multiple of 3 that you can make. Now, it could be with 1 digit, it could be with 2 digits or 3 digits. So you've got 3, 4, 8 and 7, which is the largest multiple of 3. Now, this is more of a challenging one. You could do with the cards written in front of you, really, to help you out with this one. But there's a rule for multiples of 3, so have a go at that. Okay, anybody found one yet? It's a multiple of 3. I said the largest that you could make, the number 3. Yeah, 3 would be fine. I'd be happy with 3. But is there a bigger number that you can make? Okay, so something like 48 is bigger. The largest multiple of 3. So a number that can be divided by 3 exactly. Okay, a multiple of 3. So if you count it in 3s, okay, the largest that you can make. Multiple is a word that gets confusing for children in the UK as well, a bit like factor. Okay, so the largest multiple of 3 using the digits 3, 4, 8 or 7. Okay, so as a clue, well done. Yes, very good there. Okay, so using those digits 3, 4, 8 and 7, 873 is pretty big. I'd have been very happy with 84. Now, the next question on is, well, how do you know? How can you prove that? Mathematics is about proof. How do you know that 873 is a multiple of 3? Okay, yeah, very good. 843, excellent. Okay, definite multiple of 3 and a big number as well, so well done. Okay, you see how it opens it out. Okay, it allows you to explore. It's slightly investigative. There is not one answer. Gives you a chance to have a go. Now with children, if the child had come up with the number 48 because they knew that 48 was a multiple of 3, I'd be delighted. I'd give them some support and, yeah, do you think you could make it with 3 digits? And so on. Eventually, when the students reach the age of 9, 10, 11, teaching a rule of divisibility is part of this. And the rule of divisibility for multiples of 3 is that the digits must total 3 or 6 or 9 or a multiple of 3. And so once you know that rule, that's fantastic. You can find any multiple of 3. Okay, so digit cards, very, very useful for actually exploring numbers, properties of numbers and so on. And the good thing is, obviously, once you've used those 4 digits, the following week, if you want to do a similar activity, you just take out some different digits, different digit cards, and let children explore. Okay, just moving on. Again, a slightly different activity, but with digit cards again. Okay, so cards that children have. Okay, and I often do this where individuals maybe come up to the front, hold the cards, okay, and you ask the simplest question, which is, with these 3 numbers as an example, which is the odd one out? Is it 12? Is it 8? Or is it 9? Okay, so which of these is the odd one out? Not the odd number. It's quite useful to distinguish between odd number and odd one out, but which one is different to the other 3? Okay, so we think 8 is the odd one out, and obviously the big question then is why? Why? Why is 8 the odd one out? Why not 9? Why not 12? So look at the 3 numbers. Very good. Okay, so 12 and 9 are multiples of 3, which we've just covered. 8 isn't. So I would say, yep, 8 is the odd one out. But can't we get 12 as the odd one out, or 9? Have we got another reason? Is there a reason why 9 could be the odd one out? Very good. Yes, 12 could be the odd one out. Why? Again, prove it. And it's a wonderful activity for children to actually have some sort of debate over properties of number and reasons why a number might be the odd one out, or a shape, or whatever. So, yep, 12, the odd one out, because it's got 2 digits. Okay, so 12 is different to the others. Excellent, very good. So 9 is an odd one out because it's not a multiple of 2. Okay, it's an odd number. Fantastic. Some research done in the UK with this particular activity, used as an assessment at the end of a period of work on an aspect of mathematics. They actually found that this simple activity was one of the best ways of assessing a child's understanding if they could explain the reason why a particular number or shape or measures or whatever was the odd one out. I've actually used it in English as well with characters from a book. 3 characters, 3 different characters, which is the odd one out? You know, maybe 2 male and 1 female, or 2 from one family and 1 not, or 2 who are evil and 1 that's a good character, and so on. It's a nice, simple activity. Okay, and it involves thinking skills. It involves some sort of reasoning within it. Okay, and I'm going to use another activity which involves reasoning as well. Always, sometimes, or never as a question. Okay, and the whole idea of this is for children to actually prove a statement. So for this example, the difference between 2 odd numbers is an even number. Is that always true, sometimes true, or never true? Okay, so the difference between 2 odd numbers is an even number. Is it always true, sometimes true, or never true? You can type that in, always, sometimes, or never, or A, S, or N, if you think it's true. Yes, Govi, it is, develops really good critical thinking. And I think this key one here is this idea of prove it. How do you know? So the difference between two odd numbers is an even number. Is that always true, we think? Well, how do we know? How could we prove it? What could we do to actually prove that? It is hard to say. How would we actually go about proving whether this is a true statement, that it's always true? Okay. Now with children, you give them, very good, we can use algebra to help it. With young children, it may be that they use cubes, and compare cubes, which actually comes up with 2n plus 1 equals 2n, subtracting from 4n plus 1. But that would be, that's a nice expression. But you could show that with cubes. You could actually show it on 100 square, a number line, and so on. I think with children, primary age, if they can use an image or a model to actually demonstrate a particular statement, that helps. Okay, so that's an example. I'll do another example. Okay, common misconception with children is prisms have two triangle faces. Is this always true, sometimes true, or never true? Okay, prisms have two triangle faces. I was in a classroom only last week, and there was confusion over this because many children only see one type of model. And I think making sense of mathematics is all about seeing, making connections between different models, different images, so that it actually makes some sort of sense. Now with this, it's a sometimes. Yeah? Prisms have two triangle faces. How could we actually prove it? What could you use? And I think actually practically using shapes is the key one, and looking at the end faces of a prism. The fact that they could be a triangle, they could be rectangle, they could be an octagon. Okay, and it depends on the end faces. Okay, so that one really is a sometimes, and if you're not sure, get some shapes and try it. Okay, some other packaging. Okay, another one. We'll have just two quick ones now. This one's quite useful. Rounding numbers. Okay, approximating. Many children believe that when you approximate and round a number, it rounds to the nearest 10 or the nearest 100. So what about this one? When approximating, 435 rounds to 400. Is that always true? Is that sometimes true, or is that never true? Okay, 435 rounds to 400. Okay, is that always true, sometimes true, or never true? Difficult. Okay, many children struggle with this. And again, how would you prove it? How would you prove that? For me, probably the best way is with a number line, and to actually look at 435 on a number line and label that number line to show 400, 500, 600, but also to maybe show 430, 440, 450. Okay, so 435 rounds to 400 if you're rounding to the nearest 100. But what's not clear there is, do we round to the nearest 10 with it? Okay, so it's actually a little bit about the precision of the language. And so again, it's probably a sometimes. Okay, again, precision with the language is important. Okay, it's a bit of a sometimes. Okay, again, if you're not sure, go about trying to prove it and making choices. And this one's is a good one. It's a great proof for square numbers. I worked with a group of children yesterday looking at square numbers. Is this always, sometimes, or never true? Square numbers have an odd number of factors. Okay, again, it's something that is a feature of square numbers which is often ignored. Okay, we look at properties of numbers and properties of square numbers, and we look at what's going on, but actually looking at their number of factors is a really important feature of square numbers, unique amongst numbers. Okay, and again, if you're not sure on this one, how could you prove it? Well, I think that obviously the best way of proving it is to take square numbers one at a time, to count the factors that they have. Okay, does it always come out that they have an odd number? Okay, so that type of activity involving reasoning, involving thinking, decision making from a child's point of view, it lends itself very nicely to group work as well, working in twos or threes, debating and arguing and agreeing and disagreeing, all the language that the rich language you need to make sense of the mathematics. Okay, so that type of activity is useful for it. I'm going to go back to open and closed questions, which I mentioned, because to me, I'm constantly thinking of ways of trying to make a closed question more open so that children actually engage with it. And they're not just trying to guess the answer that's in the teacher's head, which is a common thing in mathematics. This is a classic subtraction type 2-digit subtraction, which could be a closed question. This one now, by using a set of digit cards from 0 to 9 to place in those positions, those 6 positions, make it a very open activity. There are lots of different answers, lots of different ways of arranging 0 to 9 digits. Okay, and it's a nice activity to explore. One way of just adding a bit of challenge to it, and actually it's very, very simple to do, is just to add clues, to give some sort of clue to some of the numbers. So something like the digits in the second number total 7. Okay, so if we look at the numbers that there are there, the second number, which is in line with the subtraction sign, we know it totals 7. So what could they possibly be? Now remember, you're only using digit cards 0 to 9, so it limits it a little. It could be 1 and 6. Okay, it could be 3 and 4. It could be 5 and 2. So we're limiting it down a bit. What other answers could they make from those? Can you fit the others in? And you can keep going with this. Keep adding clues. The digits in the right-hand column are all even. Okay, so that changes that second number. Changes the second number to, could be 52, could be 34. Okay, it changes it slightly. And again, another clue. The difference between the digits and the answer is 3. Okay, looking at the answer, what number could that possibly be then? The difference could be 63, could be a whole variety. So it narrows it down and narrows it down. The digits in the top number total 14. Right, so that means it's double the second number. And the last one, the answer is greater than 50. We've made what we call a mystery, basically 5 clues. And if children, again, work in a group, work together on this, they can actually try and solve the mystery together. And it works so well if they have the digit cards in front of them, the numbers 0 to 9, which they can rearrange and try to follow the rules. Okay. Takes a little while. It's you know a more in-depth activity than a quick-fire calculation, but the language that's involved and the thinking is far more. Okay, and I think we're all about trying to get our students to reason and think and debate and so on. Okay, so just to show you the answer for this one, 86 subtract 34 equals 52. And if you look at the clues, the answer is greater than 50, yes. Digits, the second number total 7. The digits in the right-hand column are all even, yes. Digits in the top number total 14. And the difference between the digits in the answer is 3. So it all makes sense, it all follows. If you work in reverse, the way I wrote that one, you start off with any calculation. So with this one, I wrote down a calculation, 86 subtract 34 equals 52. And then I just made some rules that fit. I looked at the answer 52 and just made a rule. Okay, the digits, the difference between the digits in the answer is 3. So just you make the rules to fit the numbers. Okay. So opening out what is a closed, could be a closed question, opening it out to make some sort of thinking involved for the children. As an example of a closed question, 25 add 6. Okay, it's one answer. There's only one answer, and from a child's point of view, they're trying to work out what's in your head, really, trying to work it out. Okay, now just changing it slightly in format, but it means exactly the same. 25 add 6, yep, it's 31. Has only the one answer. So pyramid or bricks, okay, the 25 add 6 equals 31. If we change this around so that actually we forget the two numbers and just look at the answer, okay, now that opens it out quite nicely. So this is the most open, really. Can you give me two numbers that total 31? We've had one, the closed one. Is there a different total, two numbers that total 31? Give me an example. You can type in an example of two numbers that total 31. Very good, yep, 20 add 11, 15 add 16, that's good. Numbers that make 31. Now, that's totally open. And in the same way as adding clues, just makes it more challenging, makes it more interesting. I think just adding in a small rule as a teacher is useful. So something like, what if the number in the left-hand brick is a multiple of 2? Okay, it's an even number. Yeah, it could be 2 and 29. Okay, so we're closing it down and just slightly by adding a rule. That's good. We could then change it again. So we've got multiples of 2 in that box, so it could be any number as long as it's an even number in the left-hand side. What if the right-hand box was a multiple of 5? Can we think of two numbers that could fit in those two boxes? One is a multiple of 2 and one a multiple of 5. Any ideas? Take some thinking. Okay, very good. 6 add 25, very good. 16 add 15, excellent, excellent. Okay, so we've made it more of a challenge by putting some rules in ourselves. Now, using that as a starting point, you can then actually use it to 6 and 25 is the example we had. We could use that actually to change it to some sort of word problem. Okay, so entrance to a castle is €2 per child and €5 per adult. A group of 8 people pay €31 in total. How many adults and children are there in the group? A classic word problem, finding all possibilities type problem. Okay, and you can see how it linked back to multiples of 2, multiples of 5, total of 31. So from a very closed activity, okay, through to opening it out, through to then adding some language. but using the same mathematics. Okay. Now with children, I would encourage them to have some sort of table of results there. So again, looking at the question, you've got the cost for each child, cost for each adult, and we go back to the original question. 6 add 25 equals 31. And obviously the mathematics that's involved and the language and the thinking in a word problem, or by setting rules, is obviously a little better than 6 plus 25 equals box, a closed type question. Okay. It gives you an idea of the type of scope that you can have if you open a question out, and if you end up with closed type questions, I think children can be quite passive. They can be passive learners. If you open a question out and put the responsibility over for them, the pupils, to actually investigate, to explore, to find all possibilities. Okay, it involves more than just using mathematical skills. It involves thinking and reasoning, and we want that. We want children to be active learners, not just passively receive information from teachers. Okay. Within Macmillan Mathematics, the scheme I've written, there are those types of activities. There are a balance of activities and experiences. Certainly, exploring and practice and consolidating is an important part, but applying is a big one. Using and applying the mathematics that you've taught. I've tried to have a careful development of knowledge and skills, put it into context where necessary, because obviously it makes more sense for children if it's in a context. I try to engage thinking through problem solving. A lot of that is down to the skill of a teacher to actually give children a little time, a bit of thinking time, not always quick fire questions and so on, or closed questions, getting them to think. And most importantly, it's where I started. I think the use of vocabulary, symbols, images, diagrams and models, massively important. And I think if a child has a balance of those types of introductions from a teacher, the understanding that they get is from a teacher actually using their knowledge to try to actually explain to the children using vocabulary, images, diagrams and models, so that it actually makes sense before getting to the abstract nature of mathematics. And that's true of primary education. I do think it's also true as they get older. They need those to hang on to sometimes to make sense of the mathematics. Okay, so just from those small sort of starter activities, really, a small range, it gives you a flavour of the type of maths that I think children enjoy to explore. There are lots out there. There are lots of activities, and I think it's actually just getting the balance right, so children have the understanding, they have the practice and reinforcement, but they're allowed to explore and engage with the mathematics. Okay. I've got contact email address and website, and obviously Macmillan English has got a website with information and things. Now, such a small flavour, and I think this is the first maths webinar, certainly my first webinar. Never done one before, and the first maths one, so it was nice to have so many of you involved. If you've got any questions or anything to ask, that would be great. Obviously Macmillan Maths has got lots of ideas and things in it if you get a chance to have a look at it. Gregory has asked, can we use puzzles with matches? Some of the best mathematical puzzles that I've seen actually came from Poland. About 25 years ago, some of the Polish starting point activities were with sticks and counters. and basically setting up sequences of numbers using different shapes of sticks, and asking children to say what they saw. Really, really open type activity. And they could talk about the numbers, they could talk about the shapes, they looked at sequences, it went on to generalizing, looking at rules. Fantastic maths, and such a simple starting point. I do like mathematics when it's a simple starting point that all children can access, and very able children can take it on and on and on as far as they want. So yes, yeah, puzzles with matchsticks are great. Any other questions you've got that you'd like to ask? Oh yeah, there's a certificate of attendance you can have there, yeah. Any other questions? Has what I've said made some sense, or are a lot of you primary teachers listening in? Yeah, good question. Yeah, how to form groups of children if they have different levels. It's something that that in the UK we've had problems with because of the wide range of abilities and the importance that's put upon every child matters, and every child should reach their own ability. And that makes it very, very difficult for teachers, obviously. One of the things that I think is a key for trying to cater for different abilities is there's two ways. Differentiation by task, which is obviously giving different tasks to different abilities. I think that's quite hard for a teacher to manage, but it's an approach, and it's an approach I've used when needed. But differentiation by outcome, I think, is still the best way of managing different abilities. You give them a starting point, such as, okay, a room full of 10 people. They all send texts to each other. Okay, when they send a text to each other, how many texts is that altogether? Something as simple as that. As a starting point, all children can access. And I think that's a simple starting point, a rich activity in that way. Then children can access, use, and have a go at, which, if it's a closed task, failure comes in. If it's an open task, an open investigation, you don't often fail. Another good question, yeah, how can children learn to multiply without memorizing the multiple chart? I think memorizing is an interesting one. I think the multiple chart and the 100 square, the multiplication square, are all really useful tools for learning the multiplication facts. I think there's learning to multiply, and then there's learning the multiplication facts. Learning to multiply is more about being able to recognize the addition of groups as much as anything, or using proportionality to actually explain multiplication. So the recognition, the understanding of the concept of multiplication is a little bit different to learning a fact. I think it gets to the stage when you're 8, 9, 10-year-olds where actually you do need to just know those facts in order to access the other maths, so that you don't get yourself into, slow yourself down when you're dealing with problems. So you do need to learn the facts. There are different ways of doing that, hundreds of different ways. It could be through focusing on 2 or 3 tables for a day or a week, identifying your weak ones and practicing those, using multiplication charts, counting in different steps. Lots of different ways, and all of them, are towards the end result of just knowing that 6 sevens are 42. You do just need to know 8 sevens are 56. It's one of those. I think it's a fallacy that you don't need to learn the facts. What's wrong is that that's not the only diet the child will have or should have when it comes to multiplication. Okay, I've got to actually finish now because time's just about up. Just a question there, a book from Macmillan suggests these kinds of activities. Do look at Macmillan Mathematics, that's the key one. I'm delighted with it because it's got some quite nice pupil material, but it's also supported by a teacher's book with activities and ideas in it, and a CD with further practice and reinforcement. So do have a look at Macmillan Maths. Tell me what you think of it. You've got my email address, and recommend it to your schools if you want. Many thanks for joining in, and I hope you've enjoyed it. Bye.